Hi, I'm Ben-Yaakov. This presentation is entitled Controlled Inductor-Based BCM Buck Converters. This is a summary of a paper presented at PCIM Europe 2024 and to be indexed by IEEExplore. And the paper is by myself, Ziv Gelman, Iris Etting, Evgeny Smidochky, and the work was actually done by Ziv and Iris as part of their undergraduate engineering project at Ben-Gurion University of the Negev. The objective of this work was to improve the efficiency at low power and higher voltage of a buck converter. This is a reference design of analog device or linear technology. We have here the controller. This is a synchronous buck, 2 transistor, half bridge, and then we have the inductor. And here they're showing the efficiency. We can see that at low current and higher voltages, the efficiency drops very much. This is well known and this is very typical of many converters. And the objective again here is to improve the efficiency at this region. Now in some cases the efficiency at low power is important. And this is because first of all that power supplies do not run at nominal power all the time. Many times they are running at lower power level. Especially if we are talking about an arrangement of a redundant power supplies in which we have parallel power supplies working so that if one fails then the others are taking over. In this case, all of them will be working at lower power in the normal mode. So in some cases, higher efficiency at low power is important. Now if we look at the inductor current in a buck, or actually it's very similar in other topologies, but let's talk about buck, we can recognize between the continuous current mode, and this pertains to the current of the inductor. Here it is always positive, continuous, and then we have the discontinuous current mode in which we have part of the time the current is actually drops to 0. And in these cases, we have hard switching here. This is due to the reverse recovery of the diode. And here, it's primarily due to the output capacitance. Now, the BCM, the borderline mode, is a better choice in terms of losses, because if the current reverses and actually goes a bit negative, we can obtain here 0 voltage switching. I'm not discussing it. You can find information about this in videos in my YouTube channel. So this case is the best in terms of losses because we have here soft switching, while here we have hard. Now in BCM, the relationship between the ripple and the average current is 1:2 because the average is just about half the height of this triangular waveform. So if we are changing, say, the input voltage, then we'll be moving from BCM. Now the relationship between the input, output, and the ripple is given here. And what is important to notice is that the ripple is a function of 1/L times F, that is the inductance times frequency. So to correct for a change, you can either change the frequency or the inductance. So if we are moving from BCM, say the input becomes higher, then the ripple is higher, and then of course we'll be penetrating into the negative region more, which is not desirable. Then we can fix it by changing the frequency, increasing the frequency, or we can fix it by changing the inductance. Now, if we change the frequency, increasing it, then the losses will be higher because we have now more transitions per second, and each transition has some losses, so the switching losses will be much higher than at the lower frequency. Here, we can actually get lower frequency, so it is clear that it is desirable from the point of view of losses to change the inductor rather than the switching frequency. And indeed, this was done in this work. Here we use the design presented in this paper like 30 years ago by our group. And we have here a variable inductor, a controlled inductor, which is built around the double E core. We have a gap at the middle leg, and then we have 2 DC windings on the outer legs, and they are arranged in opposite direction such that the voltage imposed on them coupled to the AC is in opposite direction, so the AC voltage between these terminals, the DC terminal, is zero. And then because of the gap, we are starting with the given inductance, and then as the current is increasing in the DC bias, in this way, this outer rim is pushed on the BH curve toward saturation, so the permeability goes down, and therefore the inductance of the inductor will go down. And this is shown here, sort of illustrated. With no DC, we have high permeability here on this rim here, and then we have a high inductance. With high DC current, this permeability is much lower, and therefore we have a much lower inductance. So this is the idea behind this particular design, which has been used, by the way, by many workers in many studies. There are many papers that demonstrate the use of this particular design. So the idea is to replace the fixed inductor by a variable inductor, and by feeding the proper DC bias current to adjust the inductor so that the buck converter will be at BCM. Now this is an LT-SPICE schematics of this converter, this buck converter, in which we have put here a model of a variable inductor. The inductance here is changing. Here, this is the value of this inductance, and it is a function of the DC current, which is here, and it is, in this case, assumed to be exponentially dropping with the current, okay? So this is a variable inductor, and this was used, first of all, to simulate the situation in which we are adjusting the inductor to stay at BCM. Now, the original circuit without a change in inductor behaves like that. We see here two cases: output current of 1.1 amp, output voltage 12 volt, and this is with an input voltage of 20 volt, and this is 40 volt. What we see here, that here we are at CCM, while at 40 volt, the ripple is much higher, such that we have a large part of a negative current here, which is increasing losses because there is a circulating current which does not contribute to the real power. And then we have run simulation in which we've changed the frequency or the inductance. Now, for the frequency, over the 20 to 40 volt range of input voltage for the 1.1 amp output and 12 volt output, then we need to change the frequency between, say, 200 to about 400 kilohertz. If we change the inductance, then we have to change the inductance between 17 to 27 microhenry. This will be in the range to maintain BCM over this 20 to 40 volt input voltage. Now, as far as the losses go, this is from simulation. We see that with the frequency change, as expected, the losses are really going up quite a bit. On the other hand, with the variable inductor, the increase is more moderate, and there is quite a bit of difference between the two at the higher voltage. Now, in the experimental part, we have used the evaluation board by analog devices, replaced the fixed inductor by a variable inductor. This is made by Hulda transformer. This is the catalog number of the inductor used. And in this case, we have a change of an inductance between, say, 10 to 35 with the range of 1 to 0, 0 to 1. As the current goes up, the inductance goes down. So this is the performance of the experimental variable inductor. And here are the experimental results. What we see here is the efficiency of the original unit, that is with the fixed inductor and fixed frequency. This is the blue one. And then we have here the efficiency with the variable frequency, which is also going down quite a bit. And here we have the efficiency with the variable inductor. This is this one here. And you can see that as the voltage, the input voltage goes up, the difference here between the efficiency is quite a bit, and it amounts to something like 3 to 4%, which is quite a bit. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.